Hey, astronomers, F Train here. Hope you're having a good week. Hope everything's going well and you're safe and well. And had an enjoyable spring break. A little different than most spring breaks that you've probably had. And it'll be interesting to see whether whether we finish the year a week early, but we'll see. Who knows? And we'll also be interested to see whether we get to go back to school. Hopefully we do, but who knows. All right, so today we are going to be talking about how do we know that there are supernovas. So oops. So first of all, we have a do now. How are elements heavier than iron produced? Write a short paragraph and be prepared to read it to the class. So I'll give you, you guys can pause, write a short paragraph, be prepared to read it to the class, okay? And give you a chance to do that later. Radio images of supernovae reveal that they are emitting synchrotron radiation, which is produced by high-energy electrons spiraling through magnetic fields. The Crab Nebula surrounds the supernova of 1054, and there are other evidences of supernovae. So what question does this raise? All right, you might want to pause, write down your question, and then see if it agrees with this question. How can supernovae be observed? All right, I'm going to give you guys a little problem to work on here. All right, what I'd like you to do is, so the Crab Nebula, which is the remnant of a supernova, is now 1.380235 parsecs in radius. And it's expanding at 1,400 kilometers per second. So in what year did this supernova occur? All right. And I'll give you a hint. 1 parsec is 3.09 times 10 to the 13th kilometers, right? So take a couple minutes and pause and see if you can work that out. See what year that supernova occurred. And then now that you've paused and unpaused, I will show you the answer. Okay, so basically if you take the radius of the supernova remnant, the Crab Nebula, convert from parsecs into kilometers, okay, and then go from divide by 1,400 kilometers per second to tell you basically how many seconds, and then convert from seconds into days to tell you how many days, and then convert from days into years to tell you how many years. You should find out that that's about 966 years ago, which if you subtract that from 2020 gives you 1054, which we mentioned is the year of that famous supernova. This is one of the most famous supernova. Apparently it was visible in the daytime. It was so bright. And the Chinese were famous. They wrote about it, over lunch and things like that. Okay. All right. How do we know that supernovae exist? Well, that's what we're going to be talking about today, are evidences of supernovae. All right. First of all, we have naked eye observations. That's one of the first evidences that we know that supernovae exist. Naked eye supernova are very unusual. There was one in 1006. There was one in 1054, 1572, 1604. 1987, which is not that long ago, but it wasn't super popular because it was in the southern hemisphere, and it was also not super bright. I mean, it could be seen with the naked eye, but it was kind of dim and not super not super spectacular like the one in 1054, which you could literally see in the middle of the day. There were other what they call guest stars in 185, 386, 393, 1181. Might have been supernovae, but we're not sure just because there wasn't the type of scientific observations that we might expect to be able to verify that. All right. How can astronomers determine whether a supernova is a type 1 or 2? This is a little bit of a review. We talked about this, I believe, in class. Believe it or not, that was a while ago. And we said that if you look at the spectrum of a type 1 supernova, notice that you'll have some silicon here, helium, oxygen. But one element that's missing is hydrogen. You see no hydrogen lines in the spectrum, whereas with a type 2 supernova, we have this strong bomber, H alpha line. Okay. And so that's how you can tell. You look at the spectrum, and if there's hydrogen, it's a type 2. If there's not hydrogen, remember the reason for that is that a type 1 supernova, type 1A, came from a basically a ball of carbon and oxygen that exploded, and there was no hydrogen there. Okay. How else can astronomers determine whether a supernova is type 1 or 2? Well, think about it, maybe pause, and you might remember we talked about something called the supernova light curves. And we said that all supernovae, the light, the brightness decays. Well, we talked about type 1 supernova, and we said that the light will decay. It'll go up to like minus 19.3, and then it'll decay in a predictable pattern. Now, a type 2 supernova has a slightly different shaped curve. Well, it's actually a lot different. And you can see if you can compare and contrast the type 1 and type 2 curves, you'll notice that, first of all, a type 2, the light forms sort of a gradual peak and then a sharp drop off. Whereas a type 1 has a brighter, sharp peak, and then it has a more gradual drop off. All right, how can light curves be used to determine distance? All right, well, we discussed this, I believe, and but I will show you this again. And looking at the light curve plot, which is on the NAAP website, you can I'll try to remember to add this as a link. But if you look at this, let's say we detect this or select a supernova. I don't know. Let's go with 1999er. And then what we do is we move the actual observed data so that it overlaps the standard light curve. And then we can see that the peak of negative 19.3 corresponded to, and if I put in this horizontal bar there, corresponded to a, it corresponded to a apparent magnitude of 14.9. So not very bright. Obviously, that would have been something that would have only been seen maybe, with the Hubble telescope or something like that. But if we then plug in the apparent magnitude of 14.9er, all right, and of course the absolute magnitude would be minus 19.4. Well, then we can see that the distance would be about 72.4 megaparsecs, 72.4 million parsecs, which is pretty far. All right. Give you another example. So if we do supernova 1993J, okay, this comes from the same thing that we were just looking at. And what you can do is go ahead and use the equation to solve. Remember the magnitude distance formula. If we solve that for d, we get d is equal to 10 raised to the power of the apparent minus the absolute magnitude plus 5, all divided by 5. And if we do that, we'll get, in this case, 10.5 megaparsecs. Okay, so now that we know how to calculate the distance using light curves, let's talk about other supernova remnants. Well, supernova fade from a visible view in about a year. So even the brightest supernovae probably were only visible maybe for a year or so. However, the expanding shell of gas can excite the interstellar medium and release X-rays. And so a nebula, which we talked about a few lessons ago, is a supernova remnant that can last literally tens of thousands of years. And, you know, we've talked about the Crab Nebula, for example, and we've seen pictures of the Crab Nebula even in the very beginning of this. And I'll show you a couple others. But those are remnants of supernovae. Here is an X-ray image of Tycho's supernova. Tycho's supernova, remember, was in 1572. It was one of the things that led him to, you know, to favor the heliocentric theory of the universe because, you know, he wasn't able to observe parallax. And so Tycho's supernova. Now, this is a X-ray image of Tycho's supernova. Now, how are we able to see this image if the light is in the X-ray part of the spectrum? As you know, X-rays are not visible. So how is it that you're able to look at this picture if X-rays are not visible? And I'll let you maybe pause and write down an answer about that. And now that you've paused and written down your answer, you should remember that we've talked about something called false color imaging. So you know, there is a certain range of wavelengths in the X-ray portion of the spectrum. And so if we just basically adjust all of those wavelengths down into the visible part of the spectrum, then you know, it's almost like just, you know, shifting those wavelengths down into the visible part. Now we can see it. They're not real colors. That's why we call it false colors, right? Here's some pictures that we have of supernova. Remember we talked about the 1006. This is a nebula. Of course, we had the Crab Nebula we talked about. We have Tycho's supernova, Kepler's supernova of 1604. And then we have that supernova 1987A, which, as I mentioned, wasn't super bright, and it was mostly seen in the southern hemisphere, so not seen by as many people as you might expect. All right, the next evidence that we have that supernovas exist is called a neutrino flood. So basically 18 hours before the supernova of 1987 was seen, neutrinos were detected in underground detectors around the world. Now, we talked a little bit about neutrinos a while ago, and we said that these particles are so light that they can pass through the entire Earth without even coming into contact with any matter. But they built these big detectors. And so occasionally a neutrino will hit one of the molecules of liquid that is in these detectors. And when that happens, it produces a little flash, which is detected by these detectors around the outside there. Now, 18 hours prior to people observing supernova SN 1987A, there were 19 neutrinos detected, okay? And that was a huge increase from the sort of the background level, or maybe you'll see like one a day or something. All of a sudden, you know, you saw a bunch of them, okay? And so this caused them to then say, wow, this might be a supernova that we're about to see. And, you know, then they started looking around, they were actually able to see this supernova. Now, you might be wondering, why could the neutrinos reach the Earth before light? Because as you guys know, nothing can travel, excuse me, nothing can travel faster than the speed of light, okay? So think about that for a minute, maybe even pause, and think about how could neutrinos reach the Earth before light if nothing can travel faster? And it's kind of like, I'm a really fast runner, right? Nobody can run faster than me, okay? I'm just hypothetically talking here. So how, if I'm the fastest runner, how could someone beat me to the finish line? Well, you might be thinking, what if they gave them a head start? Well, that's exactly what happens. So neutrinos leave the core prior to the collapse. And so they had a head start. So basically, as the core is collapsing, we have these strange things that are happening with the protons and the electrons colliding, or, you know, basically merging together to form neutrons, and the neutrinos are released as part of that. So they get a little bit of a head start. Another evidence of supernovae is synchrotron radiation. We alluded to this in the very beginning of this lesson. Supernovae have strong magnetic fields, and electrons emitted move in spirals. Anytime a charged particle is being accelerated, think of like the Northern Lights or things like that, they emit radiation of many different wavelengths. Some of those are visible, okay? And so, oh, by the way, this is a picture of an emission nebula that was sort of, you know, that shows this synchrotron radiation. Okay, finally, well, not finally, there's a couple other things. Gamma ray bursts, they're flashes of gamma rays associated with extremely energetic explosions that have been observed in different galaxies. They're the most luminous electromagnetic events known to occur in the universe. And they can last from as short a time as 10 milliseconds up to several minutes. The initial burst is usually followed by longer afterglow emitted at longer wavelengths, maybe X-ray, UV, visible, infrared, even radio. So why might a supernova emit gamma rays? Well, as you recall, the shock wave that is produced during the core collapse. So, so during this shock wave, you know, you get you know, sort of nucleosynthesis, you know, heavier elements being produced. The energy required to do that is so huge that gamma rays are produced during events such as that. Okay. So the shock and so the shock wave from the core collapse moves matter at close to the speed of light. We're talking temperatures, you know, 10 billion Kelvin, and this is where these gamma ray bursts come from. If a supernova occurred 50 light years from the Earth, the gamma rays would destroy many forms of life on Earth. Humans would have to live underground for several decades. So you think quarantine is bad. Imagine living underground for several decades. That would be pretty severe, right? Um, Now, the thing is, the closest star massive enough to explode as a type 2 supernova is 25,000 light years away. So it appears that we are safe from something like that, at least at this point. Okay. Other remnants, neutron stars, pulsars, which we'll be talking about in future episodes of this show. And of course, we have black holes. And it was actually just about a year ago. I believe it was April 10th, 2019. So a year and a week or so ago that we actually had the first photograph, or photo image of a black hole. But we've known about black holes for quite a while. But those are also evidences of supernova. And we'll be talking about black holes a lot more in a couple episodes, or a couple lessons rather. Okay, so in summary, explain to your neighbor how astronomers know that supernovae exist, and have an awesome day and have an awesome weekend. And I will talk to you guys very soon. Over now.